In April of 2015, the Kesh Foundation Spaceship Institute officially opened its doors, marking the start of a specialized curriculum in space-age technology. The student body was precisely partitioned. 250 students were accepted into a 3-year executive master's program, with another 120 students entering a condensed 1-year track. Admittance was restricted to invitation only. The objective was to train a specific group of leaders to apply new scientific frameworks to industries like medicine, energy, and space exploration. A primary area of research involved agricultural trials. These experiments tested the effects of CO2 GANs, gas in a nanosolid state, on plant development. This research operates on the theory that invisible plasma fields, rather than chemical reactions alone, dictate how a plant physically grows and matures. To test this theory, researchers set up a trial using 5 identical nursery plants of the same size and appearance. After discarding pot 1 due to pre-existing damage, 4 active subjects remained. The observation process was rigorous. Researchers tracked growth, leaf count, the condition of the foliage, the presence of pests, dust accumulation, soil temperature, and stem thickness. Irrigation was strictly controlled. All plants followed the same schedule, receiving water every 2 days for the first 2 weeks, then every 3 days for the remainder of the study. By standardizing these environmental factors, the experiment was designed to isolate the effect of the GANs material as the single variable influencing the plant's growth. The data collected at week 2 showed unexpected results. In pot 2, where a 5 milliliter GANs ring was buried in the soil, the plant developed a thicker stem and 12 leaves, but it was 1 centimeter shorter than the baseline. It also showed 1 corrugated leaf and a burnt tip. Pot 3 utilized a triangular matrix of 3 milliliter GANs bottles. This plant produced 10 leaves and grew 2 centimeters shorter than the baseline. Crucially, 3 leaves showed edge degradation, specifically on the side facing the bottles. Pot 5 featured a surface-level ring of GANs water. While its stem thickness matched the baseline, the plant only grew 8 leaves and was 4 centimeters shorter, with 1 burnt leaf tip. Then there was pot 4, the designated control plant. It stood at 13.5 centimeters, featured 2 stems, and carried a total of 19 leaves. Based on traditional growth metrics, the untreated control plant was significantly outperforming every subject that had been treated with the GANs material. This creates a contradiction. Why would the subject receiving no treatment show the most explosive growth? The explanation lies in the nature of the material itself. CO2 GANs does not interact with the plant through chemical absorption in the soil. It projects an invisible magnetic field with an effective radius of roughly 20 centimeters. Looking at the physical layout of the trial, we see that pot 4 was placed in the middle of the array, directly between pots 2, 3, and 5. Pot 4 was never a true control. Because it sat within the overlapping 20-centimeter radii of all 3 neighboring pots, it actually received the highest concentration of magnetic field energy. Aside from the layout, the researchers identified a second oversight, the absence of a day 0 baseline. No precise measurements were recorded before the GANs was first applied. Without these initial measurements, it is impossible to determine if the plant started with a height advantage or a higher leaf count due to natural nursery variation. To stabilize the trial, the researchers locked the measurements taken at week 2 as the new permanent benchmark. In a study focused on invisible forces, establishing a flawless baseline is the only way to accurately separate field effects from pre-existing conditions. This leads to a broader theory of plant morphology. A plant's physical shape can be read as a visual record of its environmental CO2 conversion rate. One diagnostic metric is the vertical separation between leaves, indicating the specific volume of CO2 the plant must absorb. The leaf tips act as conduits, regulating the flow of the surrounding magnetic field into the plant. The number of these points corresponds to energy capacity. Single-tip leaves carry less mineral energy, whereas multi-tip leaves, like parsley, map to a more complex magnetic field flow. Even the curvature of a leaf is functional. When a leaf bends toward the ground, it completes a localized magnetic circuit back to the earth. In this framework, leaves function as antennas, designed to capture and process specific magnetic frequencies. This interaction with the environment also explains why some leaves feel greasy or fatty to the touch. As leaves absorb CO2, they synthesize proteins and amino acids, which are then excreted onto the surface of the leaf. Agricultural pests are a predictable part of this cycle. Insects are biologically drawn to feed on this specific synthesized amino acid layer. Rather than a random infection, the sudden appearance of pests can be read as an indicator of high CO2 conversion in the local environment. The leaf anomalies seen in this experiment, specifically the burnt edges and rolled centers, corroborate data previously observed in separate trials on avocado plants. To test the restorative potential of these fields, researchers also applied the GANS protocol to a houseplant that was near death and completely desiccated. After surrounding the pot with a 3-bottle GANS matrix, the plant underwent a total rehabilitation, producing dense new growth and deep green coloration. For these researchers, these initial trials illustrate how sensitive plasma-based agriculture can be. By managing spatial isolation and baseline data, it becomes possible to influence plant development through the intentional manipulation of magnetic fields.